So some example problems. A hunter fires a bullet horizontally at 200 meters per second. The firing of the gun startles him so much that he drops his chewing gum out of his mouth at the same time. Which one hits the ground first, the bullet or the chewing gum? So really we're just going to draw a picture and write a sentence or two. So we're going to say that this is the chewing gum, and we know that if you drop chewing gum, it's going to fall straight down. And here is the bullet. It's going to be fired horizontally at 200 meters per second. So the bullet begins by traveling directly horizontal, but immediately gravity starts to pull it down. And so it follows this curved path towards the ground. So which one hit the ground first? Remember, the horizontal component of projectile motion is completely independent of the vertical motion. They're going to hit at the same time. Horizontal motion does not affect vertical motion. And if you want, we can look back a few pages. Here it is. If you look at this dropped object, it is falling with a constant acceleration. It's going 0, then it's going 10 down, then 20 down, then 30 down. If you look at this projectile, yes, it starts with a horizontal, and it continues to move horizontally, but its downward velocity is 0, then it's 10 down, then it's 20 down, and then it's 30 down. So if this is your piece of gum, and let's say this is the ground, it hits the ground at the end of 3 seconds. Your projectile hits the ground at the end of 3 seconds. So the horizontal motion really does not affect at all the vertical motion. Number 2, a bale of hay is dropped from an airplane to some stranded cattle. The plane flies at an altitude of 500 meters and with an airspeed of 80 meters per second. So how far downfield should the bale be dropped? So let's draw a little sketch first. So physics sketches don't ever need to be very detailed. Here's the airplane. Here's a wing. There it is. The airplane is flying at 80 meters per second. So the bale of hay, let's say it's here attached to the bottom of the airplane. And as long as it's attached to this airplane, its velocity is also 80 meters per second. So we're going to look at all of the horizontal pieces by themselves. So the horizontal velocity is constant. So the horizontal distance equals the horizontal velocity times the time. Now, I don't know the distance right now because that's what we're looking for. How far downfield? That's dx. And we do know that Vx equals 80. So here's our airplane. Somewhere down here is the cattle. This is physics, not art class. Here's the cow. So what we want to do is drop this bale of hay so that as it falls, it's also falling horizontally, and it's going to follow a curved path and hopefully land somewhere near the cow without actually hitting the cow. So let's look at the vertical component. So the vertical velocity initially is the acceleration in the y times the time. The distance in the y is 1/2 times the acceleration of gravity times the square of the time. And we do know the distance, the height, is 500 meters. The altitude is your distance in the y. So we know enough information to get started at least. Okay, so we want to know how far downfield, that's the distance in the x. So we have a formula for distance in the x. It's the horizontal velocity times the time. But I have a problem. I don't actually know the time yet. But I do know a few things. I know the height of the airplane, the altitude, and I know a formula. So let's use this formula, distance equals 1/2 at squared. 500 meters equals 1/2. Acceleration of gravity is 10 meters per second squared. And we're looking for the time. So here's t squared. So when you move this over to the other side, this is 5. So 500 divided by 5 is 100, and that's seconds squared, equals t squared. Square root of both of these tells us that this object, this bale of hay, is going to fall for 10 seconds before it hits the ground. So I come back to this formula. We know the horizontal velocity, it's 80. And we know how long it's going to be falling, which means we know how long it's going to be traveling horizontally before it hits the ground. It's 10 seconds. Time is the common piece that the vertical and the horizontal have. If the flight time is 10 seconds, that's 10 seconds of falling, that's 10 seconds of moving sideways. So our distance in the x is 800 meters. And so we're going to drop the hay 800 meters downfield. So an airplane drops a bomb. Sketch positions of the plane and the bomb at 5 equal time intervals. So to keep pictures simple in physics, we a lot of times would just draw a plane like this. Here's a plane. We're going to be drawing them at 5 equal time intervals. So here is the plane and here is the bomb. So at 1 equal time interval, so let's draw it here, same plane. Here it's dropped. Now it's fallen just a little bit. And you'll notice it's directly below the plane. 1 equal time interval later. Here it is. So it fell this far, so it's falling, maybe it's here. And you'll notice, again, it's right below the plane. Here's the plane the next time. So it was here. Here's the bomb. It's still falling. It's right below the plane. it is again. Here's the bomb. We've got 1, 2, 3, 4 time intervals. We need one more time interval. Here's the plane, and here's the bomb. You'll notice it's following the same kind of curve that everything else has followed so far, where it's going out and down. So on the next page, number 4, describe the motion of the bomb in question 3 as seen from these 3 different frames of reference. So from the plane, let's say that you are looking down through the hole in the bottom of the plane or through a window that you can see. Let's say you're right here and you're looking straight down. Here it's directly beneath you. Here it's straight down. Here it's straight down. Here it's straight down. From the frame of reference of the plane, the bomb is always straight down. It appears to be directly below. From the ground in a position off to the side. So this is the frame of reference that we drew the picture. It looks like this bomb is below the plane. Every time we look at one, the bomb and the plane are in the same line. And we would say that it is curving out and down. If your frame of reference is from the ground, standing in the line of flight of the plane. So if we were standing maybe here, looking up, the plane is coming directly at us, this would appear like the bomb is coming straight down. Number 5, a bullet is fired horizontally at a target 100 yards away. If the muzzle velocity of the bullet is 2,500 feet per second, how far has the bullet dropped by the time it reaches the target? So the first thing that we're going to do is draw a picture here. So here is the physics symbol for a gun. It is being fired, and this is 2,500 feet per second. It's being fired horizontally, and if it continued to go horizontally, it would follow this straight line until it hits the target. But we want to know how far did the bullet drop by the time it reaches the target. So we know that this is 100 yards. We know that this bullet is actually going to follow a path that looks more like this. So we want to know how far did the bullet drop. That would be this measurement right here. How far? That's a distance. Distance in the y. So let's label everything that we know here. This is a good practice for any question that's projectile motion. Do I know dx? That's the distance horizontally. It's 100 yards. Do I know horizontal velocity? Yes, 2,500 feet per second. Do I know dy? do I know Vy? So the first thing we can do, how are the horizontal and vertical related? They're related by the amount of time. The amount of time that it takes to fly from here to here is the amount of time that it takes to fall from here to here vertically. So we are going to start with the horizontal because all the information we know is based on the horizontal. Horizontal distance equals horizontal velocity times the time. Solving for time, that's distance divided by velocity. We know the distance, it's 100 yards. And we have other units that are in terms of feet per second, and we're talking about how far did this bullet drop. I think it's going to be better for us if we change yards to feet. So we know that there's 3 feet in 1 yard. And the horizontal velocity is 2,500 feet per second. So we have 300 feet divided by 2,500 feet per second. So this tells us that the flight time of this bullet is only 0.12 seconds. What we can do with this time is take it to the vertical to figure out what we need. We're looking for how far did the bullet drop. This is the formula that we want to use. Distance equals 1/2 times the acceleration of gravity times the square of the time. We're looking for dy. We know the acceleration of gravity, it's 10. And we know the time, it's 0.12 seconds. So we can plug in our numbers here. 1/2, gravity is 10 meters per second squared down, and the time is 0.12 seconds squared. So the vertical distance that it drops is 0.072 meters. Because look at our units, we had meters per second and seconds. So 0.072 meters is not a great unit. If we change it to centimeters, 7.2 centimeters, then that's perfectly fine. The question didn't specify what the unit should be. 7.2 centimeters describes it pretty well. If you wanted to change it to inches, you could. If you wanted it in feet, that'd be okay. But unnecessary conversions, it's really unnecessary.